Okay, so this is for a discussion for 2 hours, and we are very few people, so feel free to stop me at any time and discuss anything you would like, the topic. For the first hour, I will be giving high-level introduction on what is multilingual NLP, why it can be challenging to build new systems in natural language processing for new languages, even if we have some tools in English that work very well. Why still building multilingual natural language processing applications is very important, and a very high-level recipe on what should we do. Say you are now starting a new project and you are given a totally new language you have never seen. What should you do? How you should make decisions about how to build an application that you need. And then Chan will run a 1-hour exercise on specifically one of the NLP applications, multilingual sentiment analysis. Okay. So I start from monolingual NLP, and then we move to multilingual NLP. So what is natural language processing? Natural language processing is about people communicating with machines. So maybe all of you are very young. I'm sure none of you actually lived in the time these machines appeared, but do you guys know what it is? Okay, so this is the first computer. So this is a first computer that looks like perfo cards. So you take a card and you make 80 holes in this card, and many cards is a program that you write, a computer program. So to communicate with the machine, when computers appeared, you needed to understand all the internals of the machine and speak in machine's language. Then high-level programming languages appeared. And these programming languages already resembled somehow human language. But to speak with machines, people needed actually to understand machines' language. And crucially, this language is very well structured. It does not have ambiguities. And this is how it is still different from human language. So this is the kind of communication with machines that we expect to see today. And I'll let you, actually, it's kind of, I would prefer to see your faces to see if we're speaking with each other. So this is a kind of a dialogue system, right? Or conversational agent that we expect to have today. And we communicate with machines in our language. So let's discuss what kind of language technologies do we need to build a conversational agent? So what do you think? What NLP kind of components or language technology components are in this system? So feel free to speak up without raising your hand. So what is the first component? So I take a Siri. Does everyone know what Siri is? You can, okay, I can see at least 2 of you. I speak with the Siri. What do I start from? When I speak, my voice is being recorded, right? So we have a component that is responsible for speech recognition, right? So we take these sound waves, right, and convert them to language. Then, let me open the list. So we start with speech recognition. Then to build this technology, we need some component that is related to language analysis. So we need to understand what are the words, to analyze the words, to maybe do analysis of structure, to analyze part of speech tags, and then to understand meaning of the sentence. Right? So all of these components are components of NLP that you have been discussing in this bootcamp. And one of those components you will be focusing on during your kind of internship. Then there is a component that is related to dialogue processing. So if you look at this sentence, no, I need a reservation for 2. It does not make sense without understanding the whole flow of the dialogue, right? So there is some contextual component, understanding of the context of the conversation. Finally, there is some tasks that needs to be retrieved. So for example, here, there should be some reservation. And this is related to information retrieval. And finally, for the Siri to give you a response to your request, there should be generated a sentence, and this sentence should be converted into human language, synthesized into actual speech. So we have a speech recognition component, language analysis component, dialogue processing component, possibly optionally information retrieval, and then speech synthesis, when we take a language and convert it into a speech signal. So I think speech synthesis you're going to discuss next, actually, in the afternoon. So when we talk about multilingual NLP, what I will be talking is primarily about these 2 components, specifically when we take human language, text, and analyze it and build tools to analyze it. And we can think about natural language processing. There are as 2 large group of tools that we are building. One is core technologies. So this is our backend, the pieces of our technology that will be composing the big applications that end users see. So we can talk about language modeling, how to estimate probability of a sentence, understanding the syntax, understanding some conceptual categories of language, recognition of names, recognition of mentions, and so on. And there are applications. Those are big applications that are end user applications. For example, machine translation. And several of you mentioned that you want to work on machine translation or dialogue systems such as Siri. And here are some examples. So machine translation, and currently there are many translated pairs. So how many of you actually used Google Translate? Okay, thank you. Another example of an application is sentiment analysis. So sentiment analysis, when you have a sentence, and this is a supervised classification task, when you build a classifier that given a sentence or a chunk of text, you need to decide whether this text is positive, negative, or neutral. So some kind of affective analysis. And there are other applications, for example, text summarization. So when you do a Google search, you can have a snippet that summarizes many documents to explain to you actually information that is spread across many large documents concisely. So how well does, and note that I start from English, but we will now move, after understanding what are the challenges in English, we will move to understanding why challenges in converting these applications to multiple languages are actually very serious. So how well do these systems work in practice? So how many of you heard about neural network, deep learning? Okay. Caitlin raised hand to thank you. So thanks to this revolution, deep learning revolution, with the rise of deep learning, NLP had made a breakthrough in and of many kinds of end user applications. So maybe you have seen in the news that there is NLP, machine translation achieves human parity in English or Chinese, Or maybe you have seen in news that speech recognition works so well that it's already maybe on par or better than how people recognize recorded language. And these systems, maybe you guys are also using Siri, and it works very well. But crucially, most of these applications work very well for resource-rich languages, for languages for which we have large amounts of resources and annotated corpora. And the deep learning can work only if we have a huge amount of resources. Now, this situation is different when we talk about languages that don't have sufficient resources. And this is something that we will be talking about more. But there are, even in English, there are challenges. So you can see example of how in practice these dialogue systems work still in English. So what we imagined when we talk about dialogue agents, for example, we imagine something like we saw in the movie Her. How many of you saw this movie? So it's a completely fluent conversation. In practice, this is a snippet from a paper that was published just 4 years ago, so relatively recent. Dialogue systems have made advancements, but they're still not very far from this example. So, basically their answers are not creative, a little bit boring, and also don't take into account a large context of the conversation. So if you look at this conversation between two dialogue systems, where are you going? I'm going to the restroom. See you later, see you later, see you later, see you later. So the conversations are not as sophisticated and not as interesting as we would want to. And the reason is because it is very, very difficult to build good natural language processing systems that actually understand human language. Because if you can think what you actually can express in language, being able to understand the language is like being able to understand everything about the world. And in particular, there are several reasons why language processing is very, very complex, even before we move to multilingual natural language processing. So first, language consists of many layers of structure. And we as people, we don't explicitly, and we learn this implicitly, and we operate very well, especially when we speak in our native language. But to be able to process language properly, we actually need to understand a lot of components about the language, from most shallow surface level components, like surface level text or speech that we process, and then many many layers of structure of how language works. So, starting from, and let's think what are kind of applications are relevant for each level of structure. So we start with a surface level, and I talk with you, and you hear sounds, right? And where sounds are useful, in like how in NLP we can process sounds, in what applications? So for example, when we do speech processing, right? Or when we do pronunciation modeling, we need to understand and analyze sounds. Then we can talk about individual words. So words are already units of meaning. And when we analyze words, we would build language modeling applications, for example, to estimate the probability of this sentence. And we will think about how to tokenize this sentence to individual words. And in English, it is simple. For example, we can just tokenize this sentence by looking at the white spaces. And then we can build applications that particularly focus on words, for example, spelling correction. Then we can talk about morphology. So what are individual forms of a single word? So for example, the word is. What are other forms of the word is in English? Tanmai. You're a linguist. I want you guys to start participating a little bit.
You asked other words for is.
Yeah, what are other forms? So, and of other forms for the word is.
So the past form would be was.
Right.
You could also have are for plural.
Great. So morphology is a part of linguistics that discusses what are possible forms of individual words, right? We can look at different forms, like the form of the word is, what is a form of the word is in the present tense versus past tense. We can talk about what suffixes and prefixes are added to the word when they're in different forms, so on. So this is morphological analysis is responsible for this. Then we can talk about how to tokenize words. Do we append or separate prefixes or suffixes? How to lemmatize individual words. Then we can talk about more complex analysis, syntactic analysis. So this is something that you, I think, discussed with Lori already yesterday. So this is the words, and we can have abstract categories on each word that, for example, correspond to parts of speech on the syntactic roles of these words. And the NLP task that is responsible is part of speech tagging. Next, we can look at more complex structure of the words to understand actually maybe the recursive structure, what are phrases in the words, and the syntactic parsing, and those learns to extract syntactic structure from sentences. And we can do semantic analysis. In semantic analysis, we can think about the tasks such as named entity recognition to detect individual names in a sentence, word sense disambiguation, and semantic role labeling, and so on. So I guess many of you heard these keywords, since many of you are not new to natural language processing. And finally, we can talk about discourse, pragmatics, relationships between the sentence and other sentences in the corpus or in the text. So why NLP is hard? So there are many layers of processing. And then at every layer, there is a lot of ambiguity in languages. So for example, there is ambiguity in individual words. So the word bank can correspond to a financial institution, right? Or a river bank. And then when we read the sentence and we read the word bank, we understand, as people, we understand from the context, the meaning, the individual meanings of the words. But it is not easy to build applications that actually know how to disambiguate meanings of the word. And then there are, every word can have, many words can have several parts of speech. And there is a syntactic ambiguity. For example, a sentence, I can see a man with a telescope. So how many interpretations of this sentence can you think about? Who has a telescope?
It could be, we have the telescope and we're seeing the man, or the man actually has the telescope.
Right, so there is ambiguity. So syntactic parsing will give us all possible trees, or for example, the most likely tree to resolve this ambiguity of actually with the phrase with a telescope to what word it attaches. And also there are, most sentences have actually multiple ambiguities. So the sentence, I saw her duck, has at least 3 interpretations. So I saw her duck, the duck of this woman, or I saw her duck, if the duck means duck, and I saw her duck when we are talking about this saw. And the second reason, and now we start already multilingual natural language processing, NLP is hard because of the linguistic diversity. So how many languages are there in the world? Who thinks, yeah.
I know some estimates.
You know some estimates. Who else? Does everyone knows estimates? If somebody doesn't know, I want you to try to guess. Okay, Kathleen raised your hand. That's Kathleen.
About 7,000.
Good. You're guys very advanced. I would ask, what do you think? Is it more than 20? Is it more than 50? But you already know. So there are more than 6,000 languages in the world, or about 7,000. So it's difficult. The exact number is difficult because the separation between languages and dialects is not always clear. And also there are many small languages that are not well documented and so on. So linguistic diversity of the world is actually very, very rich. If we think about individual countries, so for example, Papua New Guinea, only in Papua New Guinea, there are 839 languages spoken in individual countries. In Nigeria, there are 526 languages. And overall, you can see that these languages, languages of Papua New Guinea, languages of Indonesia, Nigeria, India, when I showed you, when you think about examples of NLP that works well, such as good conversational dialogue agents, dialogue systems, they are likely not to work well for those languages. Okay, so there are millions of speakers of languages for which we don't have enough resources, and we don't have good enough NLP tools to build tools such as machine translation or dialogue systems. So there are so when we want actually to provide solutions such as conversational agents, we want to build solutions for Spanish that has 500 million speakers, and for Hindi that has 600 million speakers, and for Swahili that has about 100 million speakers. But in practice, these tools work very well, maybe for 10 or 15 languages. So now, not all of these 7,000 languages are entirely different. There are language families. So there is Niger-Congo language. There are about 13, I think 13 language families. And each of them has from 1,000 to few hundred or few dozen languages. So we could group languages by language families, but it means that it is absolutely impossible to build one language technology that works for everything, because the languages in these language families, they are typologically very different. So it is important to understand that when we build a dialogue agent for English, a dialogue agent for Spanish does not come for free. We do not just replace input sentences or replace training data using the same system, and there will be a dialogue system that works well. There are, even to build a dialogue system for English, many resources were spent, many millions of funding dollars, and also in terms of number of people working, there was a huge effort to build a system, for example, in English. And then when we want to build a similar system in Swahili, probably even more resources needed to be invested, because we don't have good enough annotated data and years of research, for example, on Swahili, like we have years of research and understanding of what to do with English data. And when we start talking about linguistic diversity, and we now go again over the same example of the simple sentence, we see that things become much more complicated. NLP becomes more complicated. So for example, for words I mentioned, so this is a simple sentence. And when we want to do tokenization, this is the first step in building an NLP application. We just want to take an input and split it in two sentences, for example, or lowercase it, or reduce some noise if we crawl data, from example, from internet. But when we talk about tokenization in English, maybe it is clear what to do. We treat every word separated by white spaces as individual words. And this is not a perfect processing. But what do we do with Chinese? So Chinese does not have white spaces. How do we know how to separate the sentence into individual tokens? This is another example. In Hebrew, Hebrew is a very morphologically rich language. And it can have prefixes and suffixes, individual words that are concatenated to form the word. And then it is not clear how to tokenize. And I will be talking about it later. But for now, I want to ask you a question. Why do we want to split a sentence into individual tokens? What do you think? So
I think,
yeah, go ahead.
To have a standard unit of meaning.
To have a standard unit of meaning. Yeah, this is the right answer. And the answer that I would give, which is, I guess the implication is the same as you said, Kathleen, is to reduce sparsity in processing language. So if we think, what should be a unit of processing of language? So if we build a machine translation system, what would happen if our machine translation system learns to translate individual sentences and actually memorizes the translation of each sentence? There will be a very large...
It won't be...
Yeah,
it
go
won't
ahead.
be able to generalize.
It won't be able to generalize. And there will be a huge sparsity, right? Because every sentence is different. If you heard about the zip flow, there is 20% of frequent words and then 80% of much more rare words. And there is an infinite number of words in a language. Words are added all the time. So we can expect to have millions and millions of sentences, and every sentence will be different. So we don't want to build the systems at the level of sentences or paragraphs on full texts, right? We would want to split and have, as Kathleen said, smaller units of meaning, which we're processing to reduce sparsity, which will make our statistics much more trustworthy. So when we start doing multilingual NLP and we work with different language, the first question that we should ask is, how do I do tokenization? What does a word mean in this language? And what are signs and what are algorithms, for example, in Chinese, when we don't have white spaces, to split sentences into individual words? Then I have several examples from Hebrew because I'm Hebrew speaker, so it was easier for me to prepare this example. What are other challenges? When we process words, for example, Hebrew is a Semitic language. We read it right to left, and most vowels are left unspecified. So these are consonants like B, Bet, Taf, A, or B, T, and H. And it can mean several things. It can mean in T if the first letter is a preposition, and the TH, or it can mean her daughter if I look at the first two letters. The morpheme is but, the daughter, and then the suffix means genitive case. Okay, so most vowels are left unspecified. Particles, prepositions, definite articles, conjunctions, function words are appended to the word in the beginning of the word as prefixes or to the end of the word as suffixes, which means that there are many strings. For computer, it's just string. The computer doesn't understand that it's an individual word and with a meaning. The tokenization becomes very difficult because the way we want to tokenize these strings into individual words would depend on the meaning of the sentence. And there are many possibilities to tokenize. So for example, for one word, Veshebata, can be tokenized in 3 different ways and can mean 3 different things, okay? Next, there is an ambiguity at the level of part of speech tags. So, for example, not every part of speech tag is present in every language. So, for example, Russian is missing definite and indefinite articles. So, the cat and a cat will always be translated into a cat in Russian. So, there are no determiners. And there is no direct alignment between what is a noun in one language and what is a noun in another language. Okay, so what this means for us practically is if we have a good, strong part of speech tagger in English, it doesn't mean that it can be used easily in other languages. And the same morphology. Morphology of English is very simple. We basically have maybe ing ending, right? And we have s for plural and for third person verbs. And that's it, basically. If there is additional morphology in English, for example, the way we can compose new words. If you use Twitter, you can say, I will unfriend you, or we can compose individual morphemes, so concatenative derivative morphology. There is some morphology in English, but the other languages, when we build the tools for English that have this minimal amount of morphology, and then, for example, we want to process Russian. So, for example, in Russian, every noun has 7 cases. Each of these nouns can be singular or plural or neutral. And also they can be gender, the nouns. And then for the single word, the sentence, these are all possible forms of this noun sentence in Russian. So you can see that there is no good one-to-one alignment between, for example, how we treat, how we build NLP tools for English and what would we do to handle morphology in English and how would we transfer it into Russian. And then when we think about machine translation, we need to take care of agreement, right? So subject, verb, and object, for example, has to agree in case, in gender, in number, and so on. And handling this agreement becomes very difficult. This is another example of a language with rich morphology. Who heard about the language Quechua? Awesome. You guys are sophisticated. So there are. So this is a single language in Quechua. This is an extremely morphologically rich language, and this is a single word that means so they really always have been kissing each other then. And each of these individual morphemes has its own meaning. So to be able to build NLP for Quechua, you need to understand actually how to split this word into individual tokens. Linguistic diversity also is present in syntactic forms, and this is typically different across groups by language families. So if you look, for example, at Japanese and English, and here is a Japanese sentence and an English sentence, and the line mean word alignment. So here is a translation of this English sentence into Japanese, and we aligned to what word the word he translates, the word to what words the word adores translate, and so on. So we can see that the word alignment and the structure, whether it's subject verb object language or subject object verb language, and the alignment of words and the translation of individual words are very different between the two languages. And finally, there is a huge linguistic diversity in the way language groups meaning concepts into units, into words. So for example, for colors, individual cultures described colors in different ways. And when Japanese has hundreds words for colors, Russian maybe has just few, maybe just 10. And there are also idioms and metaphors that cannot be translated literally. So when you build a machine translation system and you have an input sentence, it's raining cat and dogs, how would you translate it in your native language? Who knows what is it's raining cats and dogs? You guys are native speakers, many of you. I'm not a native speaker.
It means to rain very heavily.
And then how would you translate it into, you said you speak Hindi?
Yeah. So I'm not aware of a specific construction for this, but I would just translate it literally.
It's raining heavily, right?
Heavily,
but if we naively build a machine translation system that would just translate a sentence word by word, this translation would not have any meaning, right? Okay, so there are about 6,000 languages, and processing of these languages is very, very different. And crucially, there are thousands of language varieties. So when we talk about English, there is not one English. There is no American English, right? Or not only Britain Queen's English, right? There are thousands of different Englishes. So my English is an English of native Russian speakers English. Your English is a little bit different from my English. There is American English, Scottish English, and there is Hinglish, which is a mix of English and Hindi. And each of those have different distributions of words, different ways to express meanings, a little bit different grammar. And this is why when we even build, this is also a part of multilingual NLP. When we build a dialogue system for a newspaper American English, will it work well for African American English? Probably not. So this is why also building multilingual NLP systems is very important, because we want them to be equitable and accessible to people who speak different languages, but also different dialects and different varieties of language. So in particular for English, how many different Englishes are there? So there are millions of speaking Englishes living here, but also in India, in Africa, in Australia, and in Europe, and these are quite different Englishes. And this is an example from Twitter. So if you look at Nigerian English, and if you look at Queen's English. So if you try to take your dialogue system and run it on this tweet, are you a wizard or what? Gansev. In the morning you tweet, afternoon you tweet. Nan gan they tweet better. Get your IT placement with Twitter. So if you try to run a machine translation system on this tweet, it is most likely that none of these words will be actually recognized, right? Because none of these words are vocabulary words. So and code switching is actually a very pervasive phenomenon, because the majority of world speakers are multilingual speakers. And whenever two languages come in contact with each other, people start kind of using both languages to entrain, to adapt to each other in conversation. And today we don't have actually any kind of dialogue systems that mix several languages. So now, if I summarize what I discussed until now, so we have a bunch of NLP applications, and we have about 6,000 or 7,000 languages. And we have different domains. So we have Twitter, we have news, we have TED Talks, telephone conversations. And now it becomes this huge grid. And what I started from is a dialogue system. So it's a dialogue system for English. So this is just one point in this grid. But to be able to provide NLP tools for the whole world, this is actually an infinite dimensional grid, right? So there are thousands and thousands of tools that we need to build. And if you think also about non-native English varieties or various types of code switching or different styles of different people, this becomes an infinite dimensional space. So a multilingual NLP is about figuring out how to build those solutions for different people. So if you think about what do we need to do to be able to provide solutions to speakers of so many languages, we need to build tools that will be able to collapse individual dimensions. So how can we build tools that are in the individual, for example, dialogue agent that will process multiple languages in the single analyzer? Or how can we build tools that how can we build techniques that enable us to transfer across domains? Or how can we build technologies that are general enough to work not only with huge amounts of data, but also with lesser resource languages? So low resource NLP is languages and problems that lack large monolingual or parallel corpus, and they lack manually crafted linguistic resources sufficient for building statistical NLP tools. So I started by showing you an example of a deep learning system. To build such a system, we need huge amounts of examples, of training examples, because this is a supervised learning system. It will learn well also only if it has millions of examples of conversations, or in the case of machine translation, millions of examples of translated sentences. Most languages in the world don't have such millions of examples of training data. So, and how do we distinguish how well, so for example, for machine translation, several of you mentioned that you want to work on machine translation. To build a machine translation system, we need a parallel corpus. So examples of translated sentences. So for example, this is a snippet from Harry Potter, and I think it's English Portuguese. We will take the two books and we'll translate, and we'll try to align sentences from the two books side by side. And then we can build a machine translation system by learning how to translate individual words and phrases from examples in parallel data. And when we talk about resource-rich language pair, to build a good machine translation system, we need a few millions of parallel sentences. But for most languages, we don't have this amount of resources. And then how can we evaluate whether, for example, Google Translate works well for different languages? So what we can do is take a language that you want to kind of analyze on Google Translate, type in a sentence in English and translate it into another language, for example, French. And then you can copy this sentence and back translate it into English. And if I was able to translate the sentence into French and then back translate to English and reproduce a sentence, or maybe not exactly reproduce the sentence, but kind of to keep the meaning, the right meaning and maybe style of the sentence, this means it's a good machine translation system. So English-French is a resource-rich language pair. And you can see that if I type in a sentence, you will just have to find a way to get over it into French. And I don't speak French, but I back translate and I have the output. You will have to find a way to overcome it. It's a very good translation. We can guess that this is a good machine translation system. What happens if I run it on Swahili? So the same sentence, what is a back translated sentence? You will just find a way to get on it. So we are starting by the way, does one of you speak Swahili? Don't think so. Okay, so.
I speak Swahili.
Yeah, so is it a good translation, Kathleen? probably it's an okay translation because we were able to reproduce part of the sentence, right? But it's definitely not perfect.
Yeah, it's not perfect.
It's not perfect. And Swahili has much more resources, for example, than Yoruba. So I suspect that the machine translation system for Yoruba is even much worse. And here is another example of how English Hindi, for example, translation into Hindi works. And then Telugu, which is even lower resource than Hindi, and Uzbek, which is a lower resource than Hindi and Telugu. And if you read this kind of output sentences, it becomes worse and worse, almost unintelligible. So you can see that the less training data we have, the less resources we have, the less our kind of opportunities to build off-the-shelf good systems. So we need to incorporate more data or information from other languages to be able to handle lower resource NLP for lower resource languages. And what I showed is just translations of very short words. And if you think about real world translations, so for example, an average sentence length in Wall Street Journal is about 40 words. So if I put longer sentences for translation, I guess there is a very little chance that the sentence, that we will get any kind of reasonable translation. Okay. I have just 5 minutes, so I want to give a couple of examples why we actually want to build good NLP systems. So this is something that I mentioned, that so this image shows how many people have access to internet, and basically this means that there are some resources, text resources that we can collect through by crawling, for example, Wikipedia, or communication of people on Twitter. And you can see that countries like Africa and South Asia have much less access to internet. And these are the countries which have millions or billions of users, or billions of people, and to whom NLP technologies would provide access to education, access to information, access to communication. This is why it is so important. And crucially, these are places where there is a huge linguistic diversity, that we really, to build the good NLP system, we need to build good NLP systems for 6 different language families and 2,000 languages, for example, in Africa. And in India, there are 460 languages and also 1.38 billion of people. So by building a good multilingual NLP system, we can actually address the needs, the educational needs, the access to resources for billions of people. So these are applications for social good, educational applications, emergency response applications, opportunities also to preserve languages that are going to become extinct. And this is something like documenting the culture, different cultures. So also of long-term historical impact that we can make by building good NLP systems. And here is one example in practice how low resource NLP can be helpful. So for example, in emergency response applications. So this is the actual application that was done by a company that focused on building NLP technologies for social good, for helping people. So in 2010, there was an earthquake in Haiti. And the buildings are old, the kind of the structures are old, but the cell towers are relatively new. So after the earthquake, the houses collapsed, the resources were destroyed, but cell towers remained functional and people had their phones. And then the messages start to stream in. So I cannot translate these sentences. So here is an English translation. My family is in Carrefour. Quote, we need food and water. Or here are people trapped. Or General Hospital has not enough supplies and so on. So what this company did was actually running various NLP tools, how to detect individual entities, how to detect numbers, how to detect location, to be able to address the needs of people who were trapped in buildings. And also what they could do is also identify messages of places that could help these people. So for example, Sacré-Cœur Hospital, which located in village of Okap, is ready to receive those who are injured. Therefore, we are asking people who are sick to report to that hospital. So if you can build quickly, rapidly NLP for this language, if you can identify named entities, if you can interpret kind of meaning of these sentences, of these short messages, and this is what this company did, they actually were running kind of an operation to save people that were trapped. And I will skip this other example. Okay, so this is just something that I have already mentioned. Why standard techniques, like we build a large deep learning system, cannot be simply applied to languages like Yoruba. The reason is that to build such techniques, we need huge amounts of training data, annotated or partially annotated data. And it turns out that most languages actually don't have such resources. So one example is Shanghainese. I don't see the number, spoken by 14 million people. And this is a spoken language that does not even have a written form. So in this case, you would want to be able to build NLP resources for Shanghainese. You would want to start with speech processing, and then, for example, add an NLP tool such as analysis of language and then translation and so on. And the second is that language specific engineering is expensive. So we do need a lot of resources to be able to build NLP tools for every new language. And kind of a high level summary, and Chan, I will take 2 more minutes and then I transfer to you. A high level summary, say you have this new language. Who knows what is this language?
It's the heptapod language from Arrival.
Right, yeah. I should have prepared a more difficult presentation. I see you're not beginners. Okay.
Well, what is the language on the left, though?
Huh?
What was the language on the left?
It was, I'm trying to remember, it was from another movie. I had it in my notes, but I forgot. It's from another movie. Hi, Adonis, I didn't know you were here. Okay, so what do we do if we want to process a new language that we haven't seen yet? First of all, we need to understand what language it is, right? We need to understand, I would just go to the websites like Ethnologue or WALS to read about this language and understand the structure of this language. Does this language, what are units of meaning of this language? What are words? Does it require special segmentation or tokenization? Does this language have vowels written? Is it a phonographic language, which means it's written the way we hear it? How complex is the morphology of this language? Will it require us separate pre-processing to understand what are bound morphemes? Will it require us to do special lemmatization? how to split these individual tokens into meaningful morphemes. Then what is the syntax of this sentence, of this language? So what is a structure? What is a word order? And in general, what is typology of this language? To understand what are other languages that maybe have a lot of resources, what are other languages that are similar to this language, which we could use to borrow resources or to transfer resources from resource-richer languages. So are there sufficient resources? For this, you could Google or look in Linguistic Data Consortium, or to write an email to Corpora Request, where many NLP actually researchers are signed up, or to look at ACL ontology. If there is a lot of resources, and if you happen to find the training data for that language, you can use standard supervised approaches. And these are approaches that I suspect you will be learning during the bootcamp, not during the bootcamp, but definitely during your internship. Next, say there is no supervised data, no annotated data. Are there relevant data from other languages? Maybe there is relevant data from related languages. In this case, if yes, we can build the bridges that connect between the relevant language and our target language. And for this, for example, you would go to this website, Opus Linkfill UUCE. This is a very large repository of parallel corpora. How to find parallel corpora, how to take, I showed the example of parallel corpora a few slides ago, how to find a sentence level translation between our target language and the source language for which we actually have resources. And if we are able to bridge between the two languages, for example, we could use transfer learning or multilingual learning approaches to kind of leverage resources, to bring resources from resource-rich language into resource more poor language. If there is no resources, does this language has at least large monolingual corpora? Can you go on internet and scrape Wikipedia, news, or Twitter data, any kinds of discussion of just monolingual raw text? In this case, you could build maybe some semi-supervised or unsupervised approaches. For example, build better word embeddings that could be later used with less annotated data. So this is kind of a recipe that you could use. You're asking what are there sufficient training data? If yes, use supervised techniques. They tend to work better than unsupervised approaches. If there are no sufficient training data, let's see if there are relevant resources. If there are relevant resources in other languages, can we find alignment? Can we somehow bridge between related languages? If yes, let's build transfer learning or joint multilingual approaches. If no, are there monolingual corpora? If there are monolingual corpora, can we build good word embeddings? Or can we take a subset of this monolingual corpora and build annotated data? And then from this annotated data, we could build maybe supervised approaches. And if there is nothing, if there is no relevant training data, no monolingual corpora, almost no monolingual corpora, then maybe you need to figure out how to collect data. And there is actually, you met David Mortensen, he actually did the field work, and there are other researchers who actually go to various places to collect resources for languages that don't have any documentation, any available corpora. Okay, so this is a very, very high level. Unfortunately, in 1 hour, we cannot discuss multilingual NLP in depth. So this was a very high level introduction, which primarily focused on why multilingual NLP is difficult and why multilingual NLP is important. And the next step is Chan will be running an actual exercise in which you will just run a task of sentiment analysis. So here is the task of sentiment analysis. Given a sentence, you need to tell me if this is a positive sentence or a negative sentence. So let's see, Unbelievably disappointing. Is it a positive or negative sentence? Negative?
Negative.
Negative.
Yeah. The second one, is it a positive or negative?
Positive.
Positive. Okay, so
Positive.
you see, we have built, in your mind, we have built a classifier, a supervised classifier. Given a sentence, you need to tell me if it's a positive sentence or a negative sentence. So this is a task of sentiment analysis. It is a very important task. It is important task for reasons of, there is a lot of money in this task. So company want to know how good is their products. We can try to predict the stock market or election results by analyzing sentiment of tweets. Companies would want to know what aspects of their service they could improve. So this is a very important, actually very, very practical task. Unfortunately, the large majority of resources for sentiment analysis are available for English. And a large amount of research was done in English. Nevertheless, it is important to build sentiment analysis for many languages. So what Chan prepared is what kind of challenges would you have if you try to build sentiment analysis for languages other than English, which maybe need a different pre-processing or different kind of treatment of their training data. So with this, I transfer to Chan and I stop sharing. And thank you. And Chan will run now her exercise. Are you guys ready?
Yeah, thank you.
Awesome. Thank you. Yeah, Chan, you can share your screen.
Right. One question. Do we also record this exercise or not? Just want to make sure.
I think we do. Yeah, this meeting is being recorded.
It would be better if we do.
Okay. No problem. So
And,
I will.
I was gonna say, everybody has access to like Clio and a bunch of other machines, so they like everybody can run the same things in parallel if needed. Although it's probably better if where you have Python notebooks, that's even better.
Yeah, so I have my notebook on my server, like lab server, so you guys can copy that. So I will share the address here. Wait a second. On the chat. Where's chat? Right here. So here's this, and what I want you to do is, before I begin, I just wanna ask a question. So I prepared two different exercises. So one is about multilingual NLP, so about different kinds of pre-processing for each language, and we kind of go through, so for each language we train one model, so that's one multilingual NLP model for prepared, and another one is for the cross-lingual transfer, so using different languages for one target language. So using MBERT model, so that will depend a lot on what you guys want to learn and what you guys want to, so whether you guys want to do both or want to just do the pre-trained native-based one. Because since we only have an hour, I don't think, so like depending on what your need is, I can try to cut down some exercise in one notebook to do both, or we can just do one notebook fully. So what's your preference?
I think we can start with pre-processing because it's
yeah, but I just want to know if you guys want to learn about cross-lingual transfer or not using MBERT. If you guys are interested, then I can also cover that. Okay, so what you have to do first is go to the website that I shared and open this notebook, Night-based Multilingual NLP, and click File and make a copy so that you guys can have one notebook on your own, so you can edit however you want. And please rename this to your name. So in my case, I will rename this as Chan. So this is gonna be mine. Let me see if you guys are following. Okay, I see 2 copies. And 3. Is everyone following? Okay, I see Leon and Tanmai's notebook. And so, Kathleen, are you with us? Kathleen?
Yes, I am. Sorry, I'm just
No,
behind.
nope. No problem. So you're now copying the notebook? No.
I just wanted to read the message in chat. Chan, you probably didn't see. Kathleen said, "I'll vote for the cross-lingual transfer."
Oh, I see. Oh, so okay. So I will try to cut down some other exercise and the first one to cover the second one too. Right, so I think you all copied one on your own, so let's start. So you first have to, of course, execute this to load all the dependencies, all the modules you need. So this is gonna be the introduction to the data. I know you guys already, so Yulia already explained about what sentiment analysis task is. So it's as simple as binary classification. So given a text or sentence, you have to classify whether it's positive or negative. So there are other things too, like aspect based. So whether this sentence is talking about the food, or when it comes to restaurant reviews, it's food or the seating or the service or something that's called aspect based. But for now, for this exercise, we will focus on the just binary general sentiment analysis. So the data set I pulled from is called APSA Multilingual Sentiment Analysis Dataset. So that's shortened for aspect-based sentiment analysis. So if you just go to this website, they show that the different languages they have. So for example, like Arabic, Chinese, Dutch, French, Russian, Spanish, Turkish. So they cover about like 8 quite popular language, popular, rich resource language. So let's begin. So I already coded some things. So load data, you can just load the data as easy as that. And we can just print out some data stats. So it's always good to print out some stat and example of data of the data that you're using, because it could be, sometimes you can see some kind of errors or things. So it's always good to check the example and the simple statistics. So what you can see here is number of training data, number of test data, and here the third column is for the ratio of positive labels. So it's also another important thing that you have to check is whether the test set, of course, it assumes that you have access to test set, but so it's good to see if the label ratio matches across languages or the between train and test set, because if you overfit too much and your model thinks, oh, there's 70% of train positive labels, but it's not in test set, it's not gonna perform really well. But anyway, it's really good to check it, and also some kind of samples. So examples here. So this is for Arabic, this is for English, this is for Spanish, and this is for Russian, and this is for Chinese. So let's pull another one. So what can you So we actually covered a lot of them in the lecture, but what kind of pre-processing do you think is needed for any of this language? What can you observe? So I can do one. So in Chinese, you see that there's no white space. So in each character here means not always, but like about usually they present a word. So but they don't have white space. So this is one sentence without white space. So if you just use the English tokenization strategy, which just usually rely a lot on the white spacing, then it will totally fail because you will just recognize this entire sentence as a one word. So that's not something we want. And as we discussed, for Russian, lemmatizing or stemming could be one important thing, because if you're looking at a word level, so this knife base look at which word is more associated with another, with positive label or negative label. So the pre-processing really matters a lot. So if we want to get a good quality, then we have to reduce the number of unigrams. So in Russian or Arabic, which are both of them are really morphologically rich, so it's really important to lemmatize it well. So another thing I noticed is you can probably not see here because it's for some reason right line, but in Arabic, it starts from right to left. You read right from left. But one thing to note is, so most of the time, you don't really have to do any kind of special handling for that because it's already handled somehow. And so you don't have to worry too much about Arabic being written from being right to left. But if you really want to read it and try to understand each example, then you might do. So yeah, it might be a little bit hard.
For the record, this is magically handled in Python 3. If you were using like in the old days, that was an issue. You needed to be careful.
Yeah, so I remember that. Yeah, that's a really good point. So in Python 2, it wasn't just written as left to right, but it's wrong because the order it should be right to left. But in Python 3, in Arabic, it's automatically handled. So it's much better now. So recommend using Python 3. That's a takeaway.
Yeah. Other things that you might want to take care in Arabic is diacritics, right? You might want to remove it because the same word can be written with or without diacritics.
Oh yeah.
And also maybe prefixes and suffixes, so handle morphology as we showed.
Yeah, so Arabic and Russian is definitely morphologically rich language, so that has to be handled.
Sorry, just a question. So in the language mapping, I could see Igbo there. Are you actually working? Is Igbo part of the languages?
Can you repeat the question? Sorry, I didn't get it.
Okay, I didn't get you. Hello?
Can you repeat the question, please?
Oh yeah.
Okay, okay. So in the language mapping, and in the language mapping, there is Igbo in the languages there.
Oh.
I want to ask.
Sorry, I just did it because I prepared one exercise to asking you to provide your own examples in your own language, any other language that you can speak other than English. But if you want to cover the second one, cross-lingual transfer one, maybe we might not have time to do this. So I will just put that language there, but no, we don't have data for that. But I was expecting you guys to fill that.
No problem, thanks.
So yeah, this is all so this I pulled from APSA dataset. So this is all languages I have. But so yeah, that's it. So I could also sample the data, because later I will compare the number of unigrams. So I just can sample each language into the same number of training data set like this. So the minimum was Chinese 1300. So I just downsample other languages too. So this is called data sample. And the first one is called data, just data. So there's that. So I prepared the second activity, but I will just skip that one because that takes quite time, because you have to input your own sentence to build your own data set, but I will skip that. But we also have other activities, so that should be fine. Or do you prefer doing it? You just have to give 20 sentences for training data set and 5 for test. I don't know. Let's not do it. Let's not do it. I think it takes more time.
Well, you can always, everybody can also just, you know, go back to it after, like, after your like this hour or like tomorrow or something, right? So.
Yeah, so that's a good point. So because you can download your Jupyter notebook, or I will keep this website up until like next week or so that you can just come back and try your own. So what you can do here is give examples here and negative label sentences here, and this for test, positive test, negative sentences, and then you can just define your new language as like Igbo or Korean or something. So you can just do that. So I will just leave it here like that. So, and then now this is the real pre-processing part. So let's see. Okay. So this is stemming. So the 3 things I already implemented for you are stemming and tokenization or segmentation and stop words. So I think you guys already all know about this because we had a class about pre-processing text. So I will just skip the explanation. So when you do activity 2, giving your own new data, own your language, you have to implement this. So you have to provide a set of stop words for your language. But for other languages, I already have pulled that from other list. So using some kind of modules, but for your own language, you might have to do that yourself. So this one, multi-stop word class, checks whether the given word in this language is stop word or not. So that's obvious. And
does everyone know what the stop words?
Yeah, I guess so. Because they had a class about pre-processing, if I'm right.
Yeah.
So
do you guys know?
Yes, we do. I'd say I do.
Okay, I saw others noting, so I will take that as yes. So the second one is word tokenization or word segmentation. So I also implement this using different kind of modules. So for English and in Spanish and Russian, Arabic, oh no, that's for stammers. So we need different modules. So when you work on multilingual NLP, that might be a little bit painful, but if you do it once, then you can reuse it anytime. But you have to pull different modules, packages to do the language specific tokenization. So for example, Chinese, as we mentioned, the relying on the white spacing would not work. So you have to, so I think as far as what I know, this package called Zieva is known for Chinese NLP processing tool package. And they kind of do whether this is a word or not, and they decide where to segment, tokenize each word. So I use Zieva for Chinese and Russian for the different one. Yeah, so I have imported all these related packages here, so you can take a look. And revisit if you want to use it again. And for Arabic, I use Arabic package. So for your own new language, you will have to come up with how to do this. So yeah. So this is, so you have to fill here what to do when a text is given and how to output the word segmented sentence. So you could, if your language also uses white space, then you can just simply use word tokenize, which is same as English one. But if your language also has white space, this word tokenize works quite well. So you can just return it without editing anything. But if you need to take care of morphology, so remove some common morphology to stem it, then you have to take care here. And another last one is stemmer. So, oh, I think I remember wrong. So this is just how you tokenize it. And the part that I just explained should go here. Sorry about that. So how you stem your language, or whether you have to remove your morphology, or what you have to do. So one interesting thing is Chinese does not need any kind of stemming, because they don't have, yeah, there's no concept of word stemming in Chinese. So after you segment each word, and that's it. So that's one cool thing. And this stemmer is from NLTK. So NLTK supports quite many language stemmers, so you can also use that. So these are 3 classes for pre-processing. So these are the examples here. So stem, I have to load this first. Sorry. I just put any dummy value and that should be good. So stem. So friend, friends, friended. So it's not like official word, but we use as friendly, or I friended him, something like that. So stemmer just normalize all these 3 words, because those are usually just one thing. So we can just stem it into one same word. So that's what stem are for. So as Yulia showed you as a slide, Russian and Arabic has really rich, morphologically rich language. So for the same for English for most, so you can have 4. I just listed 4 here, but there could be more, I believe. I don't speak Russian, so I can't really tell. But so you can see there are female form, neutral, plural, male, so all normalize into one. But it's not perfect though. So sometimes it's not really in the same format. It's all because the stemmer is not good, probably. So they kind of rely on some kind of rules. So that will, maybe this one just has some rule about removing this too, but I don't know. So there are some bad examples too, but most of the time it works quite great. So let's pull a pre-processing example. So this language and sentence, you have, you first segment it, and you also check whether it's stop word or not. And if it's not stop word, then you return the stem of that word. So this is just a simple code to do that. So so the example sentence was, Mr. Brown measured a cat this morning and it was 14 pounds. So if tokenization is working great, then you should not tokenize this Mr. Brown as a separate word because of the period, because this is one word. But as you can see, it's quite handled well. And also pounds is normalized into pound because we also stemmed it and something like that. So you don't have to worry about, so this is to show that you don't have to worry about the punctuations. So it's all.
I have a doubt about this.
Mm-hmm.
I just tried one thing. I put not in the sentence,
Mm-hmm.
and it recognized not as a stop word.
Oh, you already figured it out. So I was gonna talk about it too. So one caveat about just using stop words that is that you can remove some really important words in your own task. So not might not be important in some tasks, so that consider as stop word. But in our case, it really has really meaning, because I did like movie and I did not like movie is completely different one. But if you filter the not out from that sentence, and there's no way that your model will figure whether it's positive or negative. So that's really good point. So that's one thing that you have to be careful about when you test. So that's, wow, that's a really good point that you already recognize. So that's what I was actually gonna talk about. But if you see later, if you remove stop words, then you will see there's a performance drop mainly because of that. So now here's your activity. Add stammer word tokenized support for your language, so you can do it later when you do your own ones here. So let's do the activity 2. Here is it. So we will try to reduce the number of features. So number of unigrams. So this is without any kind of pre-processing here. So it's 3,000, 4,000, and Arabic with, so for Russian and Arabic, they're morphological rich language. So even with the same number of training samples, you have more unigrams here. In Chinese, there are less. So now what you have to do here is change this part, pre-processed sentence part, and reduce the number of, sentence. So I just added the lower casing here, text equals text lower, and let's see how many drop we have. So ignore this. So you can see that 7. So if you just lowercase everything, then in English and Spanish, you will get significantly, it will reduce the number of unigrams, but not in Arabic and Chinese, which do not have this uppercase, lowercase system. So what you have to do is implement whatever you want to hear this part and reduce this number and see how much you can reduce. So yeah, I will give you some time for that. You can use the stammers and other segment tokenizer or other things to do it. I will give you 2 more minutes, unless you guys are all done. So time's up. How many words, how many unigrams do you get after the preprocessing? Anyone show off their results? Check. Is everyone still working on it?
You can all feel free to unmute yourselves and chat
Yeah.
and everything, please.
Right. So for English, how low did you get? Again. I got 110. 110. So someone got any lower than that? Okay, I assume you guys are done because we don't have much time left. So let's move on. So I will show my experiments here. So I just use text split here, but I assume that every language has the white space to use split, but it wasn't true in Chinese. So what I did is use the segmenter, which we defined earlier, and use the words. So this is gonna be the segmented text later. And then what I did was stem. So I checked for each word, whether this is in the stop word or not. And then I stemmed it. So this is gonna be words, and then I just put it back as into sentence. And then the other things for the other stuff, it will be handled in this vectorizer. So what it does is just converting a sentence into one-hot vectors. So whether this word is here or not, so this is what vectorizes or is doing. So this is the number of unigrams in each language. So what you could try to do is, so let's say we only do the segmentation, and let's see how low we can get. So you can see that Chinese actually increased by 130. So that means, so we now actually segmented some words in Chinese. So for other languages, if you, doesn't really matter because this is coming from the lower casing. And then what I can do here is, instead of removing the stop words, we can just stem it only. And you can see that, oh yeah, just stemming reduces a lot of unigrams in Arabic, especially, and also in Russian, but also in Spanish, which also has.
Can I ask you something, Chan?
Mm-hmm.
The thing that you had before, did it remove stop words or did it keep only stop words? Right. So is this function true? Because that's why you yes. Okay.
You're right. I was wrong. So yeah, I think other parts I did that, but I just forgot to not. That's a really great point. So yeah, this is the total number. It's supposed to be total number. Before, the numbers that you saw before was just number of stop words, so it's meaningless. Sorry. So this is the number after adding stop words. So yeah, this is what we get. So you can see that for Russian, as Spanish and Chinese, so these three languages have similar number of unigrams after all the preprocessing, but Arabic and Chinese had different number of words. So the maybe concept of words do not really align well per language. So that's called isomorphism. And there are some studies about whether two languages are always isomorphic or not, and that's kind of cool. Recent researches in NLP, I think. So if you guys are interested in, there are some recent papers about that, so you could definitely take a look. Right, moving on. I hope you guys get somewhere around this number. And so one thing I want to note though is that smaller number of unigrams does not always mean it's better. So this is never meant to be used as I have to reduce this number to get a better performance. It's not, but it's just an example of how this different types of preprocessing can affect the number of how much you can normalize the text. But normalizing does not always necessarily the best and always desired thing to do. So let's move on to training actual night-based model based on the unigram feature that we extracted or normalized. So I already coded everything for you here. So train and evaluating, processing the sentence and preprocess, and predicting each given sentence. So
I have a question about this earlier thing that we did. So what's being implemented here is that it's stemming words if they're not stop words, right?
Yes.
I'm not sure if this is true, but could there be stop words which you'll recognize after they've been stemmed?
So that will depend on what kind of stop words you have. But
I
that's
was just
also
thinking that
possible.
maybe it'll be safer to stem first and then check for stop words later.
Yeah, that's also one thing you can do. Yeah, I think it's might be better that way, but depends on what kind of stop words you have. For example, I can think of an example where there is a word he in stop word, but he's or him should be also removed. Then if that in that case, you should definitely lematize it first and then remove stop words. Yeah, that's a good point. I just made it too simple, but yeah, that's a good point. Right, so here's are the codes: train and evaluating, predicting, processing. So one thing you can control here is, so there are arguments here. So you can whether lowercase it by setting this true, or if you set this to false, then it means you will not do the lowercasing. And for all other, options that I also have it here, whether to segment it or not, whether to stem it or not, and whether to filter the stop words or not. So you can just simply tweak these arguments to whether do it or not. So for now, I will turn everything on. No, everything off. So everything to false. So I won't do any kind of pre-processing. So the number you saw before would be the number of features we have, but I limited the number of features to max feature to 100. So in that case, a lot of noisy features. So we cannot use the entire thing. So we can only use the top 100 frequent word unigrams in this case. So let's train this model and you see the results here. So English is for 74 and 73, but Chinese 59. It's quite bad because, the baseline for binary classification is 0.5, right? So that's not really good. So what I want you guys to do is fill out this table. So what I just did is turning off all this thing, right? So these numbers will go to the baseline, which has zero pre-processing. So this is gonna be 76 and 73 and 93 and this. So ignore this column. And what I would do for all, you have to turn everything on. And then you just run this thing again, and you will get this number. So, but I guess we don't have time for that, so I will just give you my answer. Let me bring that. So you can just tweak all those arguments and get the, get the actual answer and fill out by your own. So here I have it. So this is what you get after filling out all those things. So what I want you to do now is give me some observation that you can tell from the results. So I will explain this table really quick. So this is turning off all the argument, this is turning all pre-processing, and this is everything minus lowercase. So this is typically called ovulation study to show how much each step affect the performance. So how important that is. So for example, I can give you one observation saying that, so in Chinese, if you don't do the segmentation, then the performance drops a lot. You can see that, right? But in other things like lowercasing or stemming, it doesn't affect much. So can you guys give one observation each, if possible, from this table, what you can tell? Okay. Who wants to start?
For English, the evaluation gets better without stop word filtering. That could probably say something about.
So that's what you
importance.
pointed out, right? So this is all I believe. So this is we'll watch it again, we'll not watch it again. And this is after processed. So we turn all preprocessing. So this entire sentence is reduced to just watch. And because these are the same, of course, the model will just say this is positive. But if we turn off the stop words here and run this thing, we can see that we'll watch it again, we'll not watch again. So we keep this not. So this is positive and this is negative. This is what we want. So if you just filter out all the stop words given from the default stop word set, then it will not work great. So that's one good observation. And can someone give another one?
All right, I think I'm gonna call names. I don't know, Leon.
So I think when you stem all the words, it reduces. Yeah, it reduces when you stem all the words. But for this language, it's quite different for ZH.
So yes, if you stem it, it reduces because stemmer is doing something, obviously. So it's something to improve from here to here. That's correct. And also you said, maybe you said ZH does not affect, does not change the results because as we said, as we saw in the codes, for ZH, there's no concept of stemming. So it will just output the same word. So it's basically doing nothing. So of course the performance would be the same too.
So ZH is Chinese, morphologically poor language. Correct. That stemmed words will be likely the same as the original words.
Correct. But morphologically rich language like Arabic, you can see that there are larger improvement than other languages. Like EN has 0.03, but here it's 0.06. So it's bigger improvement than other languages. Or is there any other observation that you can make? So one interesting thing I found is lowercasing actually has bad impact on Spanish. So I personally do not speak Spanish, but this kind of tells maybe this capitalization actually does have some meaning in Spanish. So if you remove that signal, then there's the model will some kind of lose some important signal about the sentiment analysis. So that tells something because other languages, lowercasing helped. So you can say that every language has different characteristics, so different preprocessing part should be done, and you also have to consider a lot of things in, you know, preprocessing each text in each language. So that's gonna be the main takeaway from this. And I will briefly explain about the next one using MBART to do the cross-lingual transfer. So the first notebook just explains you what you should do for each language. But recently, a lot of people are doing cross-lingual transfer, which means using Chinese example training data to predict the English test set. So you train with Chinese sentiment analysis training examples, and you predict English sentiment analysis sentences. So this is extra helpful in low resource languages because that means you can train a model with rich language, resource rich languages such as English, and then you can use this model to predict on the low resource languages. So that could be really helpful. So I prepared this thing there's not so many activity here, so you can just follow with me on what it is doing here inside of the notebook. So this is the model we will be using to cross-lingual transfer. So called MBERT. I wonder how many of you know what BERT is and also what MBERT is.
We talked about it yesterday.
Okay, that's awesome. So you guys already know what that is. So BERT, you learned it yesterday, and MBERT is just a BERT, the same architecture, but just trained with monolingual corpora in 104 languages, 104 languages. And also it has more vocabulary in different languages too. So you tokenize it, of course, that's what you learned, but expanded the vocabulary to handle all different languages. So all 104 languages here. So now what's good about this is regardless, it doesn't matter what language you put in. So it will map into the same dimension of word embeddings in the end. So you can say, I like this movie, or I like this movie in different languages, and you will still get the similar embeddings of those sentences and those words. So that's what we call language agnostic representation. So that's what you can get from this MBERT thing. So that's super helpful. That can be super helpful. So here you have it. So you have this CLS token embedding that you learned yesterday, and we will use it to classify this to positive or negative to the binary reprediction. So there are some useful resources here, and those codes below are substantially borrowed from this blog post. So you can actually take a look on this because this explains each step more detail. So I won't explain about the coding part here. So you load the part using Hugging Faces module, and I printed out this architecture just to show you what actually is. So encoder layers and output layer here. So that's pretty cool. And this is after using the BERT, the tokenizer provided from BERT. So using word piece tokenization method. So this is example for all languages we have. So this is the example sentence in Arabic, and this was in English, this is Spanish, and this is Russian, and this is Chinese. So you can see that it's quite segmented well. So app is on the same thing. So even with languages and with different languages mixed. So this, because we have one tokenizer, universal tokenizer, this can handle everything. So each token here is in the vocabulary in MBERT model, but not in just plain English model. There will be no token of this Chinese one. So if you just use BERT, you cannot handle this, but now we're using MBERT, so there's no issue there. So now you see how it looks like when it's tokenized, all these multiple languages. And this is the huge snippet of code that runs BERT model and preprocess and optimizer and everything. You can take a look later. And what I just want to tell you is this is the performance over train with Arabic and test with Arabic. So this is just a typical, so the same setup we saw before in the first one. So train and tested with the same language. And you can see that the performance is much better than the one we saw in night-based model, probably due to the effect the pre-trained language model. So now we are getting more than 81 in 8-ish performance on our languages. And what I want to do in this part is to do the zero-shot cross-lingual transfer experiments. So a zero-shot cross-lingual transfer means is you just train with English and you have not trained a model with the test set language, and you test it on some language. So there's a language A and B, and you use A as a train and B as a test. And this model has never seen the language B, but has to predict the language B examples. So that's what we call zero shot, because we haven't seen any shot in the target language. So what I have here is, this is the transfer language. So this is the training language, and this is the target. We also call target or test language. So we just train with Arabic and we test on English, and we train on our Arabic here and we test on Spanish. Something like that. So you can now read this table. So this diagonal would be the same thing that we saw before, but the other ones would be all zero-shot transfer learning. And I was gonna, what kind of observation can you make from this table? Is everyone following well?
Training in Spanish apparently gives better results in English than training in English.
That's a good point. So this is target language, so evaluating language, right? So, and you can surprisingly, training with Spanish data and testing on English have better, better results than training on English. So that's surprising, but it could be due to many different factors. Maybe so Spanish data has more high quality data. So maybe that was, for example, English data was noisy, but Spanish data was more, normalized well, then it will give higher performance like this. And also because English and Spanish are similar, so there are good, transfer and target language pair. So, and for example, for English, Arabic and Chinese performed less than English as Spanish, Russian, which are, Indo-European languages. But so that it kind of gives you some sense of what kind of languages you have to use for when there is one given target language. You have to be careful about choosing which language to transfer, because that will also affect the performance at the end. That's a good observation. And let's find the worst performance here. So this is the lowest number in this all table. So using Arabic translation as a transfer training language and Chinese as a test language. So this is the lowest number, kind of tell that those two languages are most dissimilar languages out of all pairs here. So this kind of things you can observe from here. So that's one fun. So we call joint training. There's a term joint training, which uses different multiple languages to train one model. So in this case, what I did was training with Arabic, English, so using all languages we have and pass on the one target language. So this is called joint training. And then what we see here is it improves a lot. Maybe we can compare this with these numbers here. Oh, sorry. I don't know where to go. Oh, okay. So let's compare with this. When you just use it in Arabic as training, but you use all other languages as a training. So you can see that it's improved by 0.01, 0.01, and also something like that. And Spanish improved a lot, and slightly, and Chinese improved a lot. So you can see that using different languages might help, but since I use all languages here, but you can also trim out some other languages. Maybe you can, for English, you can just English, Spanish and Russian instead of using all, and you can try to compare whether it's better than using all language as a training or just trimming out some languages. So choosing best transfer languages. So that's something that you can also investigate from using these things. So yeah, so that's almost all. So if you want to know more about each part of, so how I did this and everything, I will keep this thing open. So you can actually download this Jupyter notebook as an IPy notebook or Python file as well. So you can download it, or you can just come back here and just do any kind of experiment you want to do on this Google, oh no, Jupyter notebook. So it's up to you. So yeah, that's it.
Thank you,
Is there
Chan.
any question before I finish? Or anything you want to discuss? If not,
I have
yeah.
just one small question. I'm not sure how it learned. So for the zero shot thing, it trained in only one language, but it never saw the languages being tested on. Just briefly, how did it learn anything? Right? How does it know?
So it's all due to this MBERT model. So as I explained earlier, this MBERT somehow magically can, I will not use magically, but so can map is sentence into one meaning representation, right? So this encoder is basically doing that. Yeah.
It does.
So BERT is a model
language.
that is trained on huge amounts of data, that is trained together on English, on Arabic, on Chinese, on all of those languages. It just, it does not require sentiment analysis training data to train the BERT model, to train the BERT embeddings.
Okay, so if you had done this on a language which is not one of these 104 languages, then it probably wouldn't have worked.
Nope. It will not
Yeah,
work.
so BERT embeddings have representations that are shared across languages. So you train the model on English, but when you take Arabic embedding or word vector, BERT vector, the representations share a lot of information with English data, with Chinese and all other languages. And through this sharing of meanings of words, it can also kind of leverage sentiment training data in English to know which words are positive, which words are negative.
Yeah.
Yeah, so basically, yeah. So this MBERT can say, you say, I like movie and I like movie in Hindi, then it kind of can map into the same meaning representation of this too. So if you just see I like movie, but you can still make the same prediction to the Hindi version of I like movie. So if you are more interested in this paper is quite a good analysis paper, how multilingual is multilingual BERT. So you can just read this. All right, so I think that's the end of today's class. So thank you all for following well, and yeah.
Thank you, everyone.
Listening.
Have a good summer.
Thank you.
Enjoy your internships.
Thank you.
Thank you.
Thanks. Bye.
Bye.
Thank you.
Bye.